Okay, so Agda is a so-called proof assistant. It's a program which we can use to do mathematics. And the first question is, where do you get Agda? And the quick answer is, you don't install it. Instead, you use the Agda pad. If you just Google Agda pad, then it will be the first hit. And then you click here. And now you're remote controlling my server. And my server is delivering you the Emacs editor with Agda already installed and everything preloaded. If you do this, yeah, like just shown, then you will see a couple of a short cheat sheet of which commands to use. But if you do it locally, then it will more look like this. It will just be an empty window. Let me switch off the light, right, so that you can see the projector in a better way. Let's see whether I can manage to do that. I will just press random buttons. Yeah, yeah, good. Okay, that is Agda. Let me say 3 very general remarks on Agda. The first is, here at the top, you will enter Agda code. And then here at the bottom, Agda will report errors. And the goal is always to have no errors or no holes in your proofs remaining. The third remark I want to do is the following. Take care. Agda is extremely addictive. So for instance, you might know that I live in Augsburg in Germany. So the train trip was about, I don't know, much more than 12 hours because there were delays and so on. However, it felt like 5 minutes because I had my laptop with me and was able to do Agda on the train. It's really quite addictive as soon as you get used to the basics. It's really a fun tool. It's not really a proof assistant. It's more a multiplayer online game. Multiplayer because you can play it with friends. Online because it's in the Agda pad. It's not really a formal thing. It's a game. It's a fun game. Okay, and the purpose of in the next couple of minutes, I just want to give you a quick tour of some of the basics of Agda. If you then want to learn more, there are several possibilities. One is, as I said before, I don't have anything planned for the next 2 days except for giving lectures. Yeah? So we can just reconvene after lunch and do Agda or whatever. We can meet in the evening. We can meet whenever you want to. If you prefer a more asynchronous way of learning Agda, then go again on that webpage of the Agda pad and click here on the course notes for a course just concluded at the University of Padua. And there you will find exercise sheets for learning Agda, with lots of holes, which you are invited to fill in. You will also see transcripts of what we did in the sessions. And you will also have recordings of the course. Unfortunately, I did not yet get around of merging the audio stream with the video stream. Okay, so you need to play both and synchronize on your own. But there you have all the recordings. So that's one way of learning Agda, but there are even more, because at the bottom here you have a couple of references for other tutorials and introductions to Agda. Okay, and now let me just show you the first steps. Let's prove in Agda that A implies A. Okay. I wrote theorem here. That is just my name for that theorem. I could also call it theorem like that, or theorema, or important, whatever. I can also call it F. Yeah, that's just my choice of notation. And perhaps you're wondering how to enter this arrow to the right. Firstly, you don't need to. You can also write this but I argue that this is ugly to read, and Agda is supposed to be beautiful, like constructive mathematics. Hence, I will use the correct arrow, and you obtain that by just using the LaTeX command for the arrow. Most LaTeX commands just work as you are accustomed to. Okay, so F will be a proof of the fact that A implies A. Now let's actually prove that. Agda is based on constructive mathematics. So we will now work with witnesses. If you recall the BHK interpretation, there we said a witness for an implication is a uniform procedure which inputs a witness for the assumption and outputs a witness for the conclusion. So here we need to write down a function which inputs some witness lowercase x of capital A and outputs a witness of A. And that will be the identity function, f of x equals x. Yeah. So the computational reading of that is that we now have, in fact, have defined a function called f. And the definition of that function is f of x equals x. And the logical reading of that is that we prove this second A, this A to the right, by using the given witness for the assumption for the first A. Here I just wrote down the solution. Let's go back one step and write the question mark again. Question marks are valid Agda code. You can use it in order to signify holes in your development, holes which you would like to later go back to and solve them. What you then press is Ctrl+C, Ctrl+L. You don't need to remember that because in the cheat sheet it's listed at the top, Ctrl+C, Ctrl+L. L tells Agda to load the file and thereby check whether everything was correct what we wrote here. And then you will notice that Agda is complaining. Agda is complaining about the variable name A. Agda does not know about the variable name A. And in fact, we have not introduced that. In the blackboard, I would also not introduce that, but it would be informally agreed upon that I would mean for any statement A whatsoever, I would now like to prove that A implies A. And we can also do that in Agda by writing the following. And now I press Ctrl+C, Ctrl+L again, and this time it got accepted. So what this module block is doing, it's saying, for the scope of that submodule, let A be an arbitrary set. And now I'm stating that A implies A, and here I will enter the proof. Perhaps you would more like this to be something like that for any proposition A or for any statement A. Okay, I can feel that that wish of yours. Let me just lie for a second and tell you that's not true, but let me just tell you for a second that set is Agda speak for proposition. Okay, for any proposition A, A implies A. So now how do we prove it? We use that lowercase x, but let me on purpose be a little bit slower. I will press Ctrl+C, Ctrl, comma while I'm in that hole. Ctrl+C, Ctrl, comma. Again, you don't need to remember because it's listed on the cheat sheet. And then something very useful happens. Namely, Agda is summarizing below the current state of affairs. So it's stating what our goal is. Our goal is to verify A, but it's also stating what we have available in order to reach that goal. In particular, we have available the witness lowercase x of our proposition capital A. And A itself is a proposition. Okay, now I would like to fill in this hole, and I would like, and to be more precise, it's not that I myself want to do the typing. Let's see whether Agda, which is supposedly a proof assistant, is able to come up with a proof. I will press Ctrl+C, Ctrl+A. A is for the automatic mode. Again, you don't really need to remember the shortcut because it's listed in the cheat sheet. And then Agda is smart enough in order to infer that it's f of x equals x. So that is how we prove that A implies A in Agda. That's our very first step. Questions, comments, thoughts, ideas regarding these 3 lines of Agda code? I will also, by the way, upload them as soon as we are done. Let's do one more. What about the claim that A implies B? For any A and for any B, A implies B. Okay, this should not be provable because it's not the case that any proposition A whatsoever entails any other proposition B whatsoever. Let's check. I press Ctrl+C, Ctrl+, again to get hold of the context. And then Agda is informing me that our goal is B. And what do we have available? We have available a lowercase x, which is a witness for A. Okay, but using, if all you have is a witness for A, then how should you write down a witness for B, not knowing what B is? This hole can never be filled. And it's good that it cannot be filled because the implication A to B for an arbitrary A and B is nonsensical. Let's do one more. Namely, let's prove that A implies not A. A implies not A. To get the not, I'm using backslash neg for the negation sign. Let's prove that A implies not A. I load the file using Ctrl+C, Ctrl+L. But then I'll notice that Agda is complaining about negation. Apparently, negation is not defined. Might be a little bit weird, but I would actually say that it's a virtue. Agda itself is a very minimal system. The core primitives available in Agda are like 10 or so. So as soon as you've mastered 10 primitives of Agda, you know the formal system of Agda. Agda is flexible enough so that you can define all the sorts of ingredients which you need on your own. So I will now define negation in a second. I could also define conjunction, disjunction, existential quantification, and so on and so forth. All of these can and need to be defined in Agda on our own. Of course, it's getting boring to always define negation again when doing an Agda development, which is why there's a standard library containing lots of results and definitions which people have already formalized. But for now, I propose to not use that standard library so that we can learn everything from the beginning. So let me define what negation is. So negation turns a proposition into a new proposition. Negation turns a proposition into a new proposition. And yeah, what is the proposition not A? I briefly brought down the definition in the lecture. Also, we had a short break discussion about that. The definition of not phi is phi implies a contradiction. So not A is A implies contradiction. Now there's a question how to write contradiction in Agda. It's not using this English word. So on the blackboard, I used, I don't think that it works here. Yeah. On the blackboard, I used the lightning symbol for a contradiction, but that was actually a little bit informal. The proper logical symbol for contradiction is called bottom and written like that, bottom. And bottom is also not defined in Agda. We need to define bottom on our own. And we do that as follows. And then we are done. So let me explain. Firstly, this line here. Okay, this states that not A is by definition that A implies bottom, that A implies a contradiction. That is what this line is telling us. And what this is telling us is, so with that data keyword, we are introducing a new proposition called bottom. And then after the where, we would list all the witnesses for that proposition bottom. And on purpose, I did not write anything here. And I did that on purpose because I want bottom to be a proposition which is not witnessable, which doesn't have any witnesses, because it should be the false proposition, doesn't have any witness. That is why nothing is following that where clause. Okay, and now we are in a position to prove that A implies not A. Okay, how to do that? So we are given a witness of A and need to write down a witness of not A. So what is actually not A? Not A is an abbreviation for this. Okay. So now how do we prove this? Well, to prove an implication, we need to write down a uniform procedure which reads witnesses of the assumption as input and outputs witnesses of the conclusion. We need to write down a function from the witnesses of that proposition to witnesses of that proposition. So we need to write down a function. And the way we write down a function is using, if it doesn't have a name, then we use the lambda keyword. Like this. In JavaScript, the notation would be this. In Perl, it would be, it's the notation for an anonymous function. It would be like this. In Haskell, it would be like that, more or less the same as in Agda. In Python, it would be I don't, I have, does Python have lambdas? Yes. Using lambda, right? Like using this. Good. Awesome. Okay. Anonymous function which accepts an arbitrary p as input and now has the task of coming up with a witness for bottom. I press Ctrl C, Ctrl comma after putting my cursor in that second hole so that I see the context. P, the input to this anonymous function, is a witness of not A. So to be more precise, it's a procedure which turns A's into bottoms, witnesses for A into witnesses for bottom. And what we need to do is write down a witness of bottom. So writing down a witness of bottom seems hard because bottom doesn't have any witnesses. Okay, however, on the other hand, we are given this P, and we are also given that X. And these two ingredients, they allow us to, in total, paradoxically obtain a value of type bottom, a witness of type bottom. Do you see how? Say it again, a lambda? Not yet another lambda, but it's a good idea. Let me summarize the situation as follows. In the body of the lambda above, P is a witness of not A, okay, as reported by Agda here. So to be more, recalling that not A is an abbreviation, P is a uniform procedure for turning witnesses of A into witnesses of bottom. In other words, P is a function which reads as input a value of type A and produces as output a value of type bottom. So how can we use this function? How can we put this function to good use in order to fill in this hole? Say it out loud, perhaps. It might be correct. So X is of type A. X is a witness of the proposition A. And P is a function which turns witnesses for A into witnesses of bottom. What we need is a witness of bottom. Thank you very much. P of X. P of X. We just feed X as input into P. P of X. And it's more idiomatic Agda code to write P space X. Yeah, so in mathematics, in Blackboard mathematics, we write sine of pi, for instance, with a parenthesis. In Agda, to have exactly the same, we write sine space pi. We just get rid of the parenthesis. So that's our proof that A implies not A. This is a little bit confusing, and I think that's because of the multitude of negations. I would like to do examples which are hopefully less confusing. So examples in which negation does not play a central role. For instance, I would like to prove that the number 0 equals the number 0. Okay, just to get things started. I would like to prove that 0 equals 0. I get this funny equal sign using backslash and then equals equals. And if we try to do that, then Agda will complain. Firstly, about the fact that it does not know about the expression 0. That is in tune with the minimality of Agda. Agda does not have the natural numbers built into it. If we want to work with the natural numbers, we need to define them first. So let's define them. it's an infinite set, right, containing infinitely many inhabitants. But still, the definition will fit on 3 lines in Agda. The definition will be as follows. And then Agda is complaining that it does not know about the definition of inequality. Here, you write the symbol using BN for blackboard N. And then Agda is complaining about the equality symbol, that this is not yet defined. Let's define that in a second. First, I would like to spend a little bit of time on the definition of the natural numbers. The first thing to know is that Agda is not only a proof system and also not only a programming language. In fact, it's both at the same time. Agda is a unified language for writing down functions, for instance, the factorial function or the addition function or quicksort function, and also for writing down theorems and their proofs in one language. And the type, and here set here, that is not only the type of all propositions, but it also contains all the sets. And for instance, the set of natural numbers is a set. In fact, it's a new set created by those 3 lines of code. With that definition, we're introducing a new set into the Agda universe. It has the name N. And here are the possible ways of writing down inhabitants of N. There's 0 of type N. You read the colon as is of type of. And there's a successor operation, which, given a number N as input, outputs a freshly minted new number. So the inhabitants of N are 0, then suc of 0, which is the number 1, then suc of 0, which is the number 2, then suc of 0, and so on and so forth. We can also give a separate name to the number suc 0. We can call that 1. In these 2 lines, we have used Agda as a programming language. I agree that it's not a very interesting or deep program. It's just the program which applies 0 to the successor operation. But nevertheless, it's a program. Yeah? And we used Agda to write down this program. And the type of that program will be N. It's just a final result of type N. Let's implement a further function dealing with natural numbers. Let's implement the predecessor function. So the predecessor function should be a function from N to N. And it should read a natural number X as input and then output 1 less than the number X. It should output the predecessor. For simplicity, I'm ignoring negative numbers here. So I'm just declaring that the predecessor of 0 should be 0 again. Actually, it would be -1. Let's just decree that the predecessor of 0 is 0 so that we don't need to define the integers right now. So how to fill in the soul? How to define the predecessor function? Well, there are 2 cases, right? The predecessor of 0 is 0 by our definition. And the predecessor of suc of some number is that number. So let me write down, just informally for a second, my wishes for the predecessor function. My first wish is that the predecessor of 0 is 0. And my second wish for the predecessor function is that the predecessor of suc of some number a is a again. That are my wishes for the predecessor function. And it turns out that it's not only like my wishes, but that's also valid Agda code for defining the predecessor function. Indeed, I would normally never do this case distinction myself. Instead, I would do the following. Let me put that as a comment again. Write this. And now I will ask Agda to do the case split for me. Agda knows that every natural number is either of that form, it's 0, or it's the successor of some other number. Using this knowledge, Agda should be able, and is in fact able, to generate a list of all the possible cases automatically. And I activate this mode using Ctrl+C for case split. Again, you don't need to remember the shortcut because it's listed in the cheat sheet. And then at the very bottom, I tell Agda on which variable to do the case split on, in this case on x. And then Agda is generating these two clauses. It's just my personal preference to have the equality signs aligned. Agda doesn't care. Yeah, you can format that however you like. And it's my personal preference in this case situation to call that a instead of x. Good. And now in each of those two cases, we need to fill in the body of the function. So we need to say what the predecessor of 0 should be. It should be 0. And we need to say what the predecessor of the successor of a should be a. And now we have to find the predecessor function. Let's implement one more function and then get back to proofs. Okay. I would like to implement the doubling function, which reads a natural number as input and produces twice it. So pred 1 should be 2, or pred 2 should be 4. So how do we, in Agda, implement the doubling function? What would be the first step? Split the cases, right? Because in order to continue, we need to know whether x is 0 or whether x is the successor of a number. We need to know that because the result of what the double of x is depends on that situation. If you don't do a case split, then most likely we will obtain a false result. For instance, if I just declare that, then I would have falsely defined that double of any number x is 1. That is not what I intended. Okay, so let's do a case split on x. And now we need to define what double of 0 is. My definition is double of 0 is 0. And we need to define what double of the successor of x is. Double of suc of x. Do any of you have a suggestion for that? Double of the successor of x? So you imagine suc of x to be 1 plus x. So you mean this? Right. Exactly. Right? If you picture the successor as being 1 plus, so then what is twice of 1 plus x? Well, it's 2 plus 2 times x. So 1 plus 2 times x. So suc of double x. Yeah. That's how you implement the doubling function. In case you are familiar with Haskell, then you will notice that this is quite similar to Haskell. In case you're not familiar with Haskell, you're welcome. You now are learning simultaneously a little bit of Haskell. Okay, so that demonstrated Agda as a programming language. We implemented the doubling function. We implemented the predecessor function. We implemented the constant 1 simply as suc0. Now let's get back to proofs. I would like to prove that 0 equals 0. Okay, 0 equals 0. For that, I need to define the equality. And I will do it like this. I'm using a little bit of syntax here, which I'm not explaining right now, but I will later. The important thing to take out of these two lines is the following. For any set A, there is, and for any set A, and for any values u and v of A, there is the proposition u equals v. And the only witnesses of such propositions are constructed using the raffle constructor. And the raffle constructor the raffle constructor produces witnesses of propositions of the form x equals x. The point is, for any u in v, we now have the proposition that u might be the same as v, but we have a witness only in the special case, but the left-hand side agrees with the right-hand side. X equals x, the same x on both sides. Okay, and hence, here's how we verify the theorem. So we need to write down a witness that 0 equals 0. Such a witness exists. We just created it. It's called raffle. Raffle is short for reflexivity, which is like Latin-inspired English for the idea that everything should be identical to itself. Raffle. Let's prove that the predecessor of 1 is 0. Let's prove that the predecessor of 1 is 0. We can use the same proof, raffle. Because the left-hand side and the right-hand side are identical. They don't precisely look identical, right? On the right-hand side, we have the English word 0. And on the left-hand side, we have an application of the predecessor function to the value 1. However, Agda will try to simplify everything as much as possible by carrying out computations. Agda is able to carry out the computation pred1, because here at the top we have the definition of pred. And then after computing, after normalizing the left-hand side, it turns out to be the same as the right-hand side, and hence Agda will accept raffle. So you can use REFL in all those cases where by a direct computation without creativity, without any insight, just by a mere computation, you can convince yourself that the two sides of the equality are the same. Many equalities in mathematics are not results of pure computations. Most equalities require some non-trivial proof, some insight for them. We can also translate those proofs into Agda, but then not using the keyword REFL. We will need to work harder. Let's prove the following. For every number x, x equals x. Let's prove for every number x, x equals x. I will call that we'll call that theorem. Why not? We need to write down the statement of the theorem and then the proof of the theorem. Here it's only written in English. And now in hole number 1, we need to write it down in Agda notation. The Agda notation for that is as follows. This. And this is simply how you read that, yeah? So these parentheses with the arrow to the right means for every number x, and then the thing to the right of the arrow, x equals x. For every number x, x equals x. That is the logical reading. Because Agda is at the same time a proof language and a program language, this theorem here also has a computational reading. Theorem is a function which inputs an arbitrary number x, so which reads an arbitrary number x as input, and outputs a witness that x equals x, that x equals x. So, and similar to how we defined the f function or the predecessor function or the double function, we are now defining the theorem function. Let me press Ctrl+C, Ctrl+, so that we see the situation. We are given an arbitrary number x, and we need to verify that x equals x. We need to verify that by writing down a witness of the fact that x equals x. Which witness do you propose to use? REFL, indeed. And pressing Ctrl+C, Ctrl+A, so activating the automatic mode, will find that proof. When I was, let's say, a teenager, I discovered mathematics, and I really liked it. And I also discovered programming, and also liked it. And I noticed that programming and proving are similar. They attract like-minded people. Of course, there are differences, but they are kind of similar in spirit. Agda is a system which tells you that, in fact, proving and programming are one and the same. You can read this as a logical claim, as the logical claim that for every number x, it's the case that x equals x. But you can also read that as the type of a function. Theorem is a function which reads an arbitrary x as input and produces as output a witness that x equals x. You have the slightly unusual situation that the result type of this function depends on the input value. You don't have that in mainstream programming languages like Java or C. In Java and C, you also have types like int, float, double, string, char, whatever, but types may not depend on values. For instance, you don't have nowadays there are also extensions, but like in the original C and stuff, you don't have the type of integers which are larger than some number x read at runtime from the user. You have the type of all integers, and you have the type of unsigned integers or whatever, but you don't have the type of integers larger than a given value x. That would be a so-called dependent type, a type dependent on a value. Here it's the same. This here, x equals x, you can picture that as a type, similar to the type int or float or char, but it's a type which depends on a value, namely on the input value lowercase x. Okay, and computationally, this is this is the type of a certain function, and here's the body of that function. This function reads an arbitrary x as input, and then ignores that x and outputs refl, because refl is a witness that x equals x. To be more precise, programming and proving are one and the same, assuming that by proving, I mean constructively proving. If I mean by proving classically proving, then programming and proving are also the same, but only if we enrich our programming language by a certain feature, namely by call CC, by the feature of going back in time. We will learn more about that in the third lecture. For now, because we just have 15 more minutes before I think that we should go to lunch, let me define addition and then prove something about addition. So addition. I define addition by doing a case split on A, and then individually deciding what 0 plus B should be and what suc A plus B should be. So a good definition for 0 plus B would be B. And a good definition for suc A plus B would be suc of A plus B. Sometimes these two rules are also called Peano axioms. They are part of the Peano axioms for addition. If you want some motivation for the second line of definition, then let me rewrite, informally speaking, let me rewrite that as follows. Okay, that is addition. We can now, for instance, define 2 as suc of suc 0, and then verify that 1 plus 1 equals 2. Right now, Agda will complain because it doesn't know how to parse this expression, because to Agda it's conceivable that we mean it like this. We don't actually. We mean it like that. Okay, but we need to be either explicit by using parentheses, or we need to tell Agda about the different precedence levels of our addition operator and equality. We can do that. Let's not bother for now. Let's just use the parentheses. Okay, how do we prove that 1 plus 1 equals 2 in Agda? We can rephrase this as a programming exercise. How can we write down a program of this type? This is a type. And we can use as ingredients all the inhabitants which we already know that type has. And that's just this one, refl. So let's try refl, and it will work, because just by a direct computation, Agda can convince itself that the left-hand side, 1 plus 1, equals the right-hand side, equals 2. That is the situation where REFL works. Now I would like to prove a more interesting result. Namely, I would like to prove that 0 plus x equals x. That is the first proposition I would like to prove. And then later, I would like to prove conversely that x plus 0 equals x. Like this, yeah? Before continuing, we again need to supply parentheses such that Agda knows how to pass these things. And let me mention just a tiny comment, not related to our goal of proving these two propositions. We can also use the special name underscore in case that we don't want to bother with actually coming up with a meaningful name. The price for that is that we can never refer to that underscore again. But I won't have any occasion of referring to exactly that theorem. That was just an example. This is so undeep that I don't want to spend a name on that result. The logical reading of prop 1 will be for every number x, 0 plus x equals x. The computational reading will be prop 1 is a function which reads an arbitrary number x as input and outputs a witness of the claim that 0 plus x equals x. And then with prop 2 below, we have exactly the same, just reversed, x plus 0 instead of 0 plus x. And those two propositions look very much similar, right? And you know that addition is commutative regarding the natural numbers. So x plus y is the same as y plus x. So proving one should be as good as proving the other. However, Agda does not know that addition is commutative. That is something which we will be able to prove later. And in fact, it will turn out that one of those propositions is much simpler to show in Agda than the other one. The first one can be shown using REFL. Because just by a computation, Agda is able to deduce that 0 plus x is the same as x. It just needs to follow the definition up there. 0 plus b is b for any b, so 0 plus x equals x. So REFL will work. However, REFL will not work down below. Because just by doing a computation, Agda is not able to convince itself that the left-hand side is the same as the right-hand side. In fact, a computation is not useful at all. The expression x plus 0 cannot be simplified any further. If the first summand would be 0, then the expression could be simplified. If the first summand would be successor of some number, then using this definition, the expression could be simplified. But if the first summand is an arbitrary x, then there is no way to do anything. So that this proposition here actually requires a non-trivial proof instead of saying it's trivial. How do we do that proof? We need a k-split on x. We often need a k-split on the input. And now we are presented with two situations. In the first situation, x is 0. Hence, we are reduced to verifying that 0 plus 0 equals 0, which Agda already simplified for us to the goal 0 equals 0. And here in the other hole, we need to verify that suc of a plus 0 equals suc of a. Okay, how do we prove that 0 equals 0? Well, the two sides look the same, hence REFL will work. How do we prove that suc of a plus 0 equals suc a? On a blackboard, I would do a proof by induction. So we are currently in the business of verifying the proposition for suc a. And on a blackboard, I would say, well, we're doing inductive proof. Hence, we may assume that the theorem has already been proven for the old a. And now we are in the process of proving it for suc a. In Agda, what amounts to an induction on the blackboard is a recursive call in Agda. So what we are doing is we are calling prop2 recursively with the smaller input a. Before discharging the whole, let me press Ctrl+C, Ctrl., so that Agda compares what the goal is with what we have. Prop2a, so the number a applied to the prop2 function, or in other words, using this lemma in this result, in the special case of a, that is a witness of the fact that a plus 0 equals a. And what we require is almost that. What we require is a witness that suc of a plus 0 equals suc of a. That's almost the same, but not quite. We are using a certain logical principle to go from here to there, namely the principle that if you have an equation and apply the same operation on both sides, that the equation remains true. I can also write this down in Agda. We are applying the following principle. If x equals y, then also suc of x equals suc of y. Or more generally, if x equals y, then f of x equals f of y. And this principle has a name. It's called cong, for congruence. And that is what we need to use down below in order to finish the proof. It's just that Agda right now is not exacting that because lots of things have not been introduced. Let's introduce them. A and B are sets, and f is a function from A to B, and x and y are both elements of A. And then cong is a function which turns witnesses that x equals y into witnesses that f of x equals f of y. Sometimes in this line, we have been using the curly braces, like here. And sometimes we've been using the standard parentheses, like there. The difference is with the curly braces, it's an implicit argument, which we don't need to explicitly type in. Whereas with the ordinary parentheses, it's an explicit argument, which we do need to supply. So we conclude by writing down this. So that is how we conclude. And I leave it as an exercise to implement the congruence function, or in other words, to prove this congruence result. Okay. So I propose that we stop here. We will continue firstly tomorrow at the Blackboard with the second lecture on extracting programs from constructive proofs. Then in the third lecture, we will see how to transform classical proofs into constructive proofs so that we can also extract programs from that. For today, I propose the following. So I'm hungry. I would like to get lunch. Perhaps some of you also want to have lunch. Perhaps we can combine our lunch interests. And then after the fact, I will just hang around somewhere here. And if you want to meet me in order to do like one-to-one Agda tutorial or help you with the exercise or whatever, you just chat me up. In case you don't find me, contact me over Telegram or contact me over phone. My phone number is given on the webpage. And then perhaps we have a couple more hours today of Agda over constructive mathematics or whatever. It's also totally fine to do your own stuff, and then we just meet again tomorrow. It's also totally fine to never meet again. I know that all of you are busy and have things to do, so we will see. I will upload this on the webpage, and perhaps we now go